Okay, remember tomorrow is a one-day weekend, so to speak. Okay, so it's a flex day. We have no class tomorrow, no CSM classes, so not just my class. We're in meetings all day. All right, so no classes tomorrow. We will meet again on Friday. Okay. I'm already on to what 3.9, so I'm slightly ahead. Well, I'm trying to get slightly ahead so that next Thursday, I hope to make it for question and answer again. So if I can get ahead, I'll leave Thursday reserved for all questions and answers before Friday's test. But if I'm not able to do that, then so be it. We'll just go ahead and have the exam next Friday anyway. Okay, quiz on Friday will be something like 3.7. And I was going to ask you something involving velocity, acceleration, stuff like that. Okay, so maybe the closest thing to 3.7 might be, something like 7 or 8, something like that. Okay, so questions about velocity. So velocity is the first derivative. Acceleration is the second derivative. Okay, so I might ask you something about acceleration also. Acceleration is the second derivative. Velocity is the first derivative. Okay, so that would be the next quiz on Friday. Okay. All right, so I'll do a bunch of related rates problems today, and that's on the schedule. Okay. All right, so again, no school for any classes at CSM tomorrow. Meet up again on Friday. And so we are here, and I'll try to do a bunch of problems from 3.9 now. Okay. All right, so we're doing related rates. And the basic idea from related rates is we differentiate with respect to t or time. So there's always going to be a d something dt. You have to use the Leibniz notation now, the d, because there's going to be dx dt, dy dt, dv dt, dh dt, rate of change with respect to time. Okay, and now this is part of the reason why I had to use dy dx for implicit differentiation. Okay, because back then technically you could write y prime, but I was setting you up for this section where now you have to write the d notation, the Leibniz notation. Okay, so x needs a dx dt, y needs a dy dt, and so on. Okay. All right, so here we go. 3.9. Again, page 249. So for the benefit of those of you that don't have the book and aren't getting it, it's on the video. So that's up to about problem 16. And a little bit further down. And further down. Okay, and then the next page. Page 250. That hopefully. That. And let's see, I'm not even sure we have to go that far. What was the highest problem we had to go to? 37. Okay, so this is past 37, so you don't need that. All right, number 1. V is the volume of a cube with edge length x. And the cube expands as time passes. Find dv dt in terms of dx dt. Okay, so here's a very elementary situation where we're using related rates. So volume is related to length. Okay, dv dt means how does the volume change as time goes by. Dx dt, how does x change as time goes by. Okay, so I just start with the formula for the volume of a cube. If the length is x, then volume is equal to x cubed. So here we go. Volume is equal to x cubed. Okay, now, when I differentiate with respect to time. So again, every variable gets a d variable dt. V gets a dv dt, x gets a dx dt. So what's the derivative of v with respect to t? Now it's 1, but then times dv dt. What's the derivative of x cubed? 3x squared times dx dt. Okay. And that's all they asked for this one. How does dv dt change as dx dt changes? Okay. So I plug in here. If they, and later on they'll give me actual numbers, like they'll say dx dt is 5 and x is 2 or whatever. But that's all you have to do for this one. All right, so that was pretty straightforward, I hope. Okay, number 5. A cylindrical tank with radius 5 meters is being filled with water at the rate of 3 cubic meters per minute. How fast is the height of the water increasing? Okay, so using the letters, this is volume, this is time. So this is dB dt, rate of change of volume with respect to time. How fast is the height of the water increasing? That is dH dt, rate of change of height with respect to time. Okay. Please notice the difference between height. Height is a static quantity, like height is 7 meters. But dH dt, how is the height changing as time goes by? So maybe the height is changing, so the water level is increasing, right? At maybe, I don't know, 2 meters per minute or whatever. Okay, so let me show you the picture now. So I have a cylinder. It told me the radius is 5 meters. I have a certain height. I'm filling it up with water. This is how fast the water is going in. 3 meters cubed per minute. That's a cube there. Okay, so if I pour in water at the rate of 3 cubic meters per minute, how fast is the height rising? That makes sense. So as I pour in water, the height goes up. What's the rate of change of the height? Okay, so at first I have to start off with the formula for the volume of a cylinder. Okay, so how do I find the volume of a cylinder? It's the cross-sectional area times the height. Well, what's the area? Area of a circle is pi r squared. So pi r squared times h. So that's the formula for the volume of a cylinder. Okay, now in this one particular problem, r is not a constant. R is not a variable, r is a constant. They told me it's 5. So plug in 5 right here. 5 squared is 25. So volume is 25 pi h. So there we are. So that's a relation between volume and height for this particular picture where radius is 5 and it's constantly 5. Now I differentiate with respect to time. Okay, so every letter gets a d letter dt. So differentiate the left side. Derivative of v is 1 times dv dt. The derivative of 25 pi h. 25 pi is a constant. So 25 times 3.14, so 75, 76, something like that, whatever. Okay, so the derivative of 25 pi h is 25 pi times dh dt. All right, now they told me dv dt, 3 cubic meters per minute. Once you see it's divided by minute, you know it's dt on the bottom. It's a rate, related rates. So 3 is my dv dt. So put 3 over here. 3 is equal to 25 pi dh dt. Divide both sides by 25 pi. So I have dh dt is 3 over 25 pi meters per minute. Okay, so that's my answer. That's how much the height is changing as time goes by. 3 over 25 pi. You can leave it like that as far as I'm concerned, or you can put it in a calculator. It's about 1 over 25. Okay, because 3 over pi is almost 1. Pi is like 3.14, right? So 3 divided by that is about 1. So it's roughly 1 over 25 meters per minute. Okay. All right, 11 is an interesting problem. 3 variables, x squared plus y squared plus z squared equals 9. So just a quick timeout. You don't really need it here, but you'll need it a lot more. Remember, x squared plus y squared equals 9. It's a circle. Center of the origin, radius of 3. If I go x squared plus y squared plus z squared equals 9, I'm no longer in 2D, 2 dimensions, I'm in 3 dimensions. So this is a sphere of radius 3, centered at the origin. Okay? So if you're in 3D, to label a point, you need 3 numbers. Right? So we're used to x comma y. In 3 space, you have x comma y comma z. That's a major topic in Calculus 3. If you guys have to take Calculus 3, I know a lot of you have to end up taking Calculus 3. Calculus 3 is 3-dimensional calculus. Okay? So we've been used to just x and y. In Calc 3, you have x, y, and z. Okay? So x squared plus y squared plus z squared equals 9. So notice how you have to label a point. And I'll be honest with you, I forget too when I teach Calc 3, because I'm so ingrained that, oh, a point is x and y. And I forget, it's not just an ordered pair, it's now an ordered triple. So x, y, z is 2, 2, 1. Okay. But once you get to Calc 3, you'll get used to writing not just x comma y, right? You're used to just putting stuff like 2, 2, and you say, okay, that's x and y. But now in Calc 3, you're doing a lot of x, y, z. So 2, 2, 1. X is 2, y is 2, z is 1 in 3 dimensions, right? But anyway, you're given dx dt, dy dt, and it says find dz dt and all this stuff. Okay. So when I have to plug in, x is 2, y is 2, z is 1, dx dt is 5, dy dt is 4. Okay, so I'm going to leave the book right now, but I have everything that I need here. X squared plus y squared plus z squared equals 9. It's a sphere. Center of the origin, radius is 3. Okay, so I will differentiate with respect to t. So remember the game that we play, every variable needs d variable dt when we differentiate. So x has to have dx dt. Y needs a dy dt. Z needs a dz dt. Okay, every letter gets a d letter dt. Okay. So remember when we're doing implicit differentiation, right? When I differentiate with respect to x, normal derivative. When I differentiate with respect to y, I had to tack on dy dx. Okay. But now with related rates, every variable has to have a d variable dt. Okay. Oh, and here's all the data. They told me dx dt is 5, dy dt is 4, and what is dz dt? So I put dz dt equals question mark. And the x, y, z is 2, 2, 1. That means x is 2, y is 2, z is 1. Okay, so here's the derivative. They're all pretty much the same. Derivative of this is 2x dx dt plus 2y dy dt plus 2z dz dt equals the derivative of 9 is 0. So there we go. Okay, so every variable has to have d variable dt, no exceptions. Okay, so 2x dx dt, 2y dy dt, 2z dz dt. Okay. Now I plug everything in. X is 2, put that here. Y is 2, put that here. Z is 1, put that here. Dx dt, you told me was 5, that goes there. Dy dt is 4, put that here. Plug it all in and you're solved for dy dt. Okay. Even though it looks funny, dx dt, treat it like another variable. Pretend it's just another letter of the alphabet. It's like W. Okay. So even though you write dx dt, it's a variable. Same for that, same for that. Okay, so 2 times x, which is 2. Oh, I'm sorry. What did I do here? Yeah, notice here I can factor out the 2 and then divide it out. I can go 2 parentheses, all of this, and then divide out the 2. So what I did over here was just lost the 2. I lose the 2. Okay. If I factor out the 2 and then divide both sides by 2, 0 divided by 2 is 0. So I just have x dx dt plus y dy dt plus z dz dt. Okay. So did you have to do that? No. You just be multiplying everything by 2 unnecessarily, I guess. Okay, so that's 2 times 5 plus 2 times 4 plus 1 dz dt. Okay, so x was 2, dx dt is 5, y is 2, dy dt is 4, z is 1, and grind it out. Okay, so that's 2 times 5 plus 2 times 4 plus dz dt equals 0. 10 plus 8, 18 equals dz dt. Sorry, 18 plus dz dt equals 0. So dz dt equals a negative 18. So the negative means z is decreasing as time goes by. All right. Okay, so these are the beginnings, just the beginnings of related rates. Now we have some actual word problems involving related rates. Okay, so we have all these words and we have to translate it into, quite often, draw a picture so you can see what's going on, and then set up your relations. Okay, so let's try 13. Okay, a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles an hour passes directly over a radar station. Okay. Let me see if I can go like that. Okay, so let me show you the words some more. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. Okay, unfortunately, I can't show you the words and my picture at the same time, but a plane, 1 mile up, 500 miles an hour, passes over a radar station. Okay. When it's 2 miles away from the station, find the rate at which the distance from the plane to the station is increasing. Okay, so here's the picture. 1 mile up, here's a radar station, 500 miles an hour. Okay, I'm going to call this X. This is 1. I'm going to call this Y. Okay. This is 2 miles. 2 miles from the radar station means this distance. It's not straight up and down. It's this distance here. So it's asking for the rate of change of the distance as time goes by. That means I'm looking for dy dt. Find dy dt. Okay, so this is 1. This is 2. Okay. First, I did some Pythagorean theorem. X squared plus 1 squared equals y squared. X squared plus 1 squared equals y squared. X squared plus 1 equals y squared. Okay. When y is 2, put 2 here. So x squared plus 1 is 2 squared. X squared equals 4 minus 1, or 3. So x equals radical 3. So when I need to plug in of x is radical 3, y is 2. Now, for my related rates, I will use this equation. X squared plus 1 equals y squared. X is a moving quantity. Y is a moving quantity. Okay, so as the plane keeps going, X changes, and that means Y changes, right? So imagine a plane keeps going over here, right? X changes, but my new hypotenuse is way out here, right? Okay, X squared plus 1 equals Y squared. Now I take this equation, differentiate with respect to t. So just like the previous problem, what's the derivative of x squared? 2x dx dt. The derivative of 1 is 0, equals the derivative of y squared, 2y dy dt. Divide both sides by 2y to cancel, and I want to isolate the 2y. 2's cancel, so I have dy dt equals x over y dx dt. Okay, 2's cancel out, x over y dx dt. Now I plug everything in. Okay, so from the picture, x, radical 3, y is 2, dx dt, rate of change of x with respect to time. X is right here. That's how fast that's the speed of the plane. So dx dt is 500 miles an hour. So 500 goes right here. Okay, so that's the speed of the plane. Dx dt 500. X is radical 3. Y is 2 at a particular moment in time. Okay, and cancellation, 250 radical 3 miles per hour. That's considered the exact value, but you never talk that way. So it's more appropriate to punch it in the calculator and round your answer to the nearest whole number. So 433 miles an hour. Okay, so the answer is 433 miles per hour. What is that 433? That's the rate of change that we're moving away from the radar as time goes by. And you might want to know that because you're always in contact with the radar, right? So if you're over here, even though you're flying 500 miles an hour, how fast are we moving away from the radar? 433 miles per hour. And maybe you need to know that because as time goes by, you might say, okay, after a while, I can't contact the radar station, so I got to try to contact some other, radar station or whatever. Okay, so 433 miles per hour. Okay, so that's it for that one. So for a lot of these pictures, if you can, for these problems, if you can draw yourself a picture, it'll go a long way. Okay. All right, so that was 13. I will set you up for 17 now. Two cars start moving from the same point. One travels south at 60 miles an hour. The other travels west at 25 miles an hour. Start at the same place. West 25 miles an hour. South 60 miles an hour. South 60 miles an hour. West 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so this car is going west 25 miles an hour for 2 hours. This car is going 60 miles an hour south for 2 hours. So at what rate is the distance between the cars increasing 2 hours later? Okay, I call this X, Y, and Z. This is the distance between the two cars. So what is the rate at which that's changing after 2 hours? I'm looking for dz dt. All right, so let me lose the book. Okay, so you can definitely see a Pythagorean relation. X squared plus y squared equals z squared. Okay, I will need x, y, and z. 25 miles an hour, that is dx dt, rate of change of x with respect to time, 25 miles an hour. What is dy dt? 60 miles an hour, rate of change of y with respect to time. Okay. All right. Now, first thing I did was find these static quantities, these actual distances. So if I drive 25 miles an hour for 2 hours, 50 miles, right? If I drive 60 miles an hour for 2 hours, 120 miles. Okay. I can find this hypotenuse by doing the Pythagorean theorem. I'll save time for that. That comes out to be 130. Okay. By the way, some of you may have heard a Pythagorean triple, 5, 12, 13. Okay. That's a Pythagorean triple. You may have had that in trig. So if you had a 5 and a 12, some of you already know, oh, automatically this is 13, right? Another famous one is 3, 4, 5. Have you heard of 3, 4, 5? If you have this is 3, this is 4, the hypotenuse is automatically 5. Okay. So this is a variation of the 5, 12, 13 right triangle, and just multiply them all by 10. So you have 50, 120, and 130. Okay. If you don't like that, just use your Pythagorean theorem. a squared plus b squared equals c squared, and you get 130 here. So I won't take up class time for that. You know how to do that. But 50 squared is what? 2,500. 120 squared is 14400. Add them up and you get what? 16900. Whose square root is that? So anyway, I know I went fast through that, but you should Pythagorean theorem. Okay, so just like the other one, 2x dx dt plus 2y dy dt equals 2z dz dt. And then I'll just say, etc. You can plug everything in. Okay, by the way, you can get rid of the 2's. Divide by 2. X, 50. Dx dt, 25. Y, 120. Dy dt, 60. Z is 130. Solve for dz dt. In fact, once you lose the 2's, all you got to do is divide by 130 and you got it. Okay, so I'll leave you to finish the rest of that, but I've given you the essence of it. Just plug in all the numbers, solve for dz dt. Okay, your answer will be so many miles per hour. So make sure you put your answer as miles per hour. Okay, then let's see, 19 is sort of like that. The picture is a little bit different. Okay, 19, a man starts walking north at 4 feet per second from point P. Point P, 4 feet per second north. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. Okay, so here's what's happening. This distance is 500 feet. The woman is walking south at 5 feet per second. Okay, so one more time. Man is going north at 4 feet per second, starting at P. So he goes like that. At the other point, which I'm going to call Q, I made that up, Q, and it's 500 feet due east of P. So this is 500 feet. Okay, she walks at 5 feet per second, but she walks 5 minutes later. At what rate are the people moving apart 15 minutes after the woman starts walking? Okay. So I'm going to call that distance Z. It's dz dt. Okay, first I notice we're mixing up 2 units. We've got seconds, but we also have minutes. Okay, so I need to change everything to a common unit. Let's change everything to seconds. Okay, so 5 minutes later, 300 seconds, 5 times 60. 15 minutes after the woman starts walking. 15 minutes times 60, 900 seconds. Okay, now, in order to make heads or tails out of this, I decided to draw this picture here. That way I get a right triangle. Okay, so this is X, this is Y, and I'm going to call that Z, like that. Okay, so this is X, this is Y. So this is X plus Y. X plus Y, 500, and Z. All right, so dy dt is 4. Dx dt is 5. Okay, now I need to find some distances here. So what are these distances? So the woman walks 5 feet per second for 900 seconds, 4,500 feet. The man, however, walks 5 minutes more. So the man walks 20 minutes total. 20 minutes, 1,200 seconds. Okay, 1,200 seconds times 4 feet per second, 4,800 feet. Okay, so the man walks 4,800 feet, 4 feet per second for 1,200 seconds, 20 minutes. So this distance is 4,800 feet. This distance is 4,500 feet. How come? Because the woman walks only for 15 minutes, because it says she started 5 minutes later. So 5 feet per second times 900 seconds, 4,500 feet. All right, so my Pythagorean relation, take a look at this big triangle. I have x plus y squared plus 500 squared is equal to z squared. That's my relation. I plug in. Let's see, x plus y, 4,500 plus 4,800 is 9,300. So this is 9,300, that's 500. So 9,300 squared plus 500 squared equals z squared. That means z is the square root of 9,300 squared plus 500 squared. Punch in the machine, it's about 9313.43. Okay, so if and when I need to plug that in, z is that number. X is 4,500. Y is 4,800. dy dt is 4 feet per second. dx dt is 5 feet per second. Okay, so here we go. So my relation is x plus y squared equals 500 squared equals z squared. So I differentiate with respect to time. Okay, this looks like a chain rule. So how do I differentiate this? 2 times x plus y. And then by the chain rule, it's times the derivative of the inside. So what's the derivative of x? dx dt. Plus derivative of y, dy dt. Okay, so one more time, it's a chain rule. It's blah, blah, blah squared. So to differentiate that, 2 comes down, blah, blah, blah to the first power. And then by the chain rule times the derivative of the inside with respect to t. So the derivative of this is dx dt plus derivative of that is dy dt. Equals the derivative of z squared, 2z dz dt. Okay, the 2's cancel out, divide by 2, divide by z. So I have dz dt is now x plus y divided by z times dx dt plus dy dt. Now I just plug everything in because I have x, 4,500. I have y, 4,800. I have z, this 9313.43 stuff. And I have dy dt, 4. And I have dx dt, 5. So I plug all those things in. So here we go. X plus y, 4,500 plus 4,800, divided by z, that hypotenuse. And then dx dt plus dy dt, 5 plus 4. So you just plug everything in. Right? So for a lot of these problems, you start off with some relationship between 2 or more variables. That's why they're called related rates. And then you differentiate with respect to time. It's always d something dt, and then it's just plug in. Okay, punch that out. It comes out to be about 8.9 feet per second. Okay, so my answer is 8.9 feet per second. Okay. All right, then 21, and I think 21 was the last one I was going to do today. So I might have some time for questions at the end. So I'll be done in about 2 or 3 minutes if anybody wants to ask me stuff. #21. The altitude of a triangle, the height, is increasing at a rate of 1 centimeter per minute. So anytime you see that time on the bottom, you know it's going to be blah, 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 dt. So that would be dh dt. Rate of change of height with respect to time. Area is increasing at 2 centimeters squared per minute. You can kind of tell by the units, right? Centimeters squared, that's area, that's time. So that's change of area with respect to time, dA dt. Okay, at what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters squared? Okay, so I drew a picture giving all the data. Okay, let me use the book. Okay, base height. Area is 1/2 base times height. I decided to multiply both sides by 2. You don't have to do that, but I don't want to have a fraction. So it's 2a equals bh. 2a equals bh. Okay, so ultimately find dB dt, the rate of change of the base with respect to time. Now what told me that was going to be the case? Let's see. At what rate, so once you see the rate, you know it's going to be the Leibniz notation, the d stuff. The base of the triangle is changing. So find dB dt. Okay, h is 10, they told me that. A is 100, you told me that. They don't tell me the base, but I can figure it out. Okay, so area 100, so put 100 here, equals 1/2 base times height. The height they told me was 10. Half of 10 is 5. Okay, so 100 equals 1/2 base times 10. Half of 10 is 5. 100 equals 5b, so b is 20. So at the appropriate time, I'll plug in, if I need to, 20 for the base, 10 for the height, 100 for the area. Okay. So 2a equals b times h. Differentiate with respect to time. Every letter gets a d letter dt. So what's the derivative of 2a? 2 times dA dt. How do I take the derivative of BH? Product rule. First times the derivative of the second. So what's the derivative of h? dH dt. Or you can say 1 times dH dt. Plus second function, h, times the derivative of the first, dB dt. Okay, so one more time. Here I have to do the product rule. This is just constant multiply rule. Derivative of 2a is 2 times dA dt. Product rule. First times the derivative of the second. What's the derivative of the second? 1 times dH dt. Plus the other way around. Second, h, times the derivative of the first, dB dt. Now I plug in a bunch of stuff. dA dt, they told me was 2. Plug in 2 here. B, we figured out to be 20. They didn't give it to us, but I worked it out. Okay, they gave me the area, they gave me the height, plug into the formula, B is 20. dH dt, they told me it's 1 centimeter per minute. Plus h, h is 10. So just plug in. So the only number I don't plug in is dB dt. That's what I'm solving for, as you might guess. All right, there we go. 2 times 2 equals 20 times 1 plus 10 dB dt. So that's 4 equals 20 plus 10 dB dt. Subtract 20. Negative 16 equals 10 dB dt. Divide by 10. So dB dt is negative 1.6 centimeters per minute. Final answer. Okay, and the negative means the base is decreasing. The base is actually getting smaller as time goes by. Okay. So that's that one. All right, so I'm done, folks. I'll stop there. I'm not quite done with the related rates section, but that's okay. I have time next time for that. So let's see. So Friday, I'll probably be able to start some of 3.10. So I'll do maybe just one more of 3.9, do some of 3.10 on Friday, and then go ahead and give you the quiz. Okay. All right, so let me stop the share. See what we have in the chat. Okay, and thank you, Prasanna. So if anybody wants to respond to Prasanna, you may. I can't be part of that because I have meetings all day. Okay. Let's see. And, all right, so I'm assuming, Prasanna, you've got 3.6, number 9. And I'm not sure in the time that I have left if I can do it for the benefit of everybody, but let me try that. 3.6, number 9. Okay. Yeah, I can do that. I have, what, 8 minutes left? Okay. Get my clipboard here. Sorry. .6, number 9. G of x is equal to ln x e to the negative 2x. Okay, so go back to sharing the screen. Okay. So the hard way is to take it literally as it is, where you go 1 over that, and then by the chain rule times the derivative of the inside, which is a product root. Okay. Much, much easier is to use your property of logs. Okay. So first I have a product. ln of something times something is ln of the first plus the ln of the second. Okay. So I'm using this property. ln of a times b is equal to ln a plus ln b. Remember that rule? And then what do you notice about this? ln and e cancel out. ln x minus 2x. So to take the derivative of that is very easy, right? So if you use your property of logs, you can often make the problem much, much better, right? Because I can see some of you going, oh, how do you do 1 over x e to negative 2x, and times the derivative of x e to negative 2x, which is a product rule, which is first times the derivative of second plus the second times the derivative of first, blah, 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 blah. Do properties of logs and look at how easy this is. So what's the derivative? 1 over x minus 2. Done. So can you believe how easy this ends up by using your properties of logs? Otherwise, it's a much more difficult problem. Is that right? Oh, yeah, I'm still recording. So you still should be able to see this on the recording if you want to look at it later. Okay? All right, and let's see, back to here, chat. I think I'm caught up. Yeah, okay, so everybody look at the chat that Prasanna has if you want to go with that. I can't be part of it. I'm in meetings all day tomorrow, but thanks, Prasanna, for that. And I think I've caught up with the chat. So yeah, okay, anybody else with anything? Otherwise, we're done for the day. Any questions about anything, please? No? Okay, so have a good one-day weekend tomorrow, okay? And I'll see you Friday. Friday, I'll be ready for a quiz. I'll do some more related rates, but I'll get started with the next section, and then I'll give you the quiz. All right, that's it, folks. Have a good day. Have a good one-day weekend. See you on Friday.